Hi, I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm over at Logix with Cheng Wang, who's going to talk today about inferencing in AI, machine learning, and deep learning. Cheng, obviously AI, machine learning, deep learning are one of the hot topics today. Most of the work that's happened so far, though, really has been focused in on the training sets and the training side. We're now starting to get a lot more interest in development on the inferencing side. What do you have to think about? What are some of the issues that you have to worry about on inferencing?
Well, inferencing is for a completely different scale. Like a speaker a few weeks ago at the AI Hardware Summit said, inferencing used to be for the rich. Right? For training, you have no choice. You have to train your data set and solve convex optimization problems that are extremely complex, and therefore it probably only makes sense to run on CPUs and GPUs. But to do real-time inferencing on millions and millions of edge devices, it is simply far too expensive to deploy that sheer amount of CPUs and GPUs, even if they can meet the power and cost and the performance requirements, and most of the time they cannot. So really, we've opened a whole new can of worms from actually now deploying these models that we've been learning and training on, is how do we have a good way to run these models with a reasonable cost, power, and performance at a system level.
So how do you improve the efficiency from a power, performance, and area level as well?
Well, the best way is always to go to an ASIC. But you can't always do that. But if you could, for example, if you have an inference engine and you control the model and you know the model doesn't have to change for the lifetime of the product, maybe you have a simple security camera that just have to do some simple object detection that you know the model you have now is good enough, you actually build a very efficient ASIC to run that one neural network model. And that will work beautifully. But most times, most customers are not okay with a fixed neural network model. We're in the early days of neural network. Think C and C++ in the early 60s and 70s and even 80s. Nothing is fixed, and we can't just hard code a design. So we needed programmable, efficient solution.
So why don't you draw some of this out for us?
Yeah, sure. So this is an extremely simple two-stage neural network example where there's 4 inputs going to 4 neurons in the first layer, and there's some activation. Activation, it can be a number of nonlinear functions, and it will then go into the second stage, which also has 4 neurons and output, followed by the output activation layer. So this is an extremely simple network, but this network may change. One customer can come by and say, I actually want the first stage to be 4 inputs to 5 neurons. Of course, in reality, it's more like 1,000 neurons, but I'm giving you a very simple example here. Or you may say, I want them to have slightly different biases, or maybe I want these activation functions to be a different nonlinear function. There is a lot of change that can be programmed into these neural network models. And currently, they have to be run on CPUs and GPUs normally to be able to achieve this level of programmability.
And that programmability is necessary because not only is your data set changing, but your algorithms are changing as well, right?
Exactly. Your data set is changing, but that may be okay, though sometimes you will have to change the weights, in which case it may change the neural network and have to reprogram it, especially if it's sparse. But it's mostly the algorithm, because the algorithms are evolving so quickly. Every day, every few weeks, there's a new state of the art in image recognition or classification that is really hard to keep track of them all. But at the same time, we have no way of predicting by the time the product is out in the field 2 years from now what's going to be the state of the art that the customer is going to want.
There's a lot of talk about being able to speed these up by as much as 100 times over what's available today. How do you do that, and what sort of problems does that cause?
Exactly. 100 times, that gap is usually the gap between ASICs and processors, or ASICs and GPUs, and that's well known. And that's because GPUs and ASICs, and CPUs, these von Neumann processor architectures are inherently inefficient. There's a lot of memory to load, the input memory, the weights memory, and then when the output is computed, it's stored to memory, and maybe it's read again to be activated and then stored somewhere else. There is a lot of memory bandwidth, orders of magnitude more than what an ASIC will require, where much of the processing is done locally and only going to the SRAM when absolutely necessary. And that gap is what we're trying to close here.
And looked at from a different angle, really what we're doing is taking a lot of this data and condensing it into patterns, right? Because what used to be one bit in and out of memory is now let's do multiple things at once.
Yes, exactly. So a lot of it is actually efficient memory usages. So for example, if I were to load this byte out of memory, I can actually process, all 4 of these neurons in parallel. So once you have a more parallel hardware, a lot of these memory accesses can be made much more efficiently.
And instead of reading data in just one way, left to right, for example, you're now reading it left to right and up and down in a full matrix, right?
Yes, and not just that, in an ASIC or an FPGA, which is really the closest you can get to an ASIC, there is many ways to, have one data access radiated to a number of mostly very localized processing elements, and those will be processed and then stored to localized memories. For example, you can think of a simple data flow where the outputs of these, when ready, can be stored to some small localized memories, in which case they will be reloaded or read by the next layer to perform the next set of operations. There's not much of redundant reads or remodified writes happening in an ASIC-like architecture.
What makes that architecture better for inferencing than training?
For training, there's actually not much we can do because just the sheer size of this optimization problem just makes it better, more suitably run on a software like a CPU or a GPU. But for inferencing, we are basically solving a math problem. There's no more optimizations to be done from an algorithm perspective. We're simply trying to find the cheapest, most efficient way of executing a certain math problem. And that is usually most efficiently done on an ASIC or ASIC-like hardware, like an FPGA.
So you're going from brute force parallelism into more architecture, microarchitecture to try and perfect this.
Yes. Instead of having thousands of GPU cores, which is what you would call brute force parallelism, this is basically, exploiting the native parallelism of the gates themselves or of the neurons themselves and mapping them natively, to, an ASIC-like architecture. And you will see in our MX designs, it's basically a very interesting combination of ASIC-like neural network accelerators connected by an FPGA-like interconnect fabric. And that's what gets to, in our opinion, the best of both worlds in inferencing.
So where does this go next? How do we speed all this up, make it even more efficient? Does it require new memory types? Does it require new architectures as well?
I think it really comes down to how do we stay as close to ASIC as possible while providing this full layer of programmability that allows implementation of arbitrary neural network models. And that's what our MX tile is trying to achieve. It really has most of its processing, heavy weightlifting done on ASIC-like hardware, but it has a control circuitries and some of the inputs and output processings, pre-processings, and memory accesses done in the FPGA-like circuitry, so it's fully programmable layer by layer of the neural network. In our opinion, it really gets to the best of both worlds.
And as we go forward, this is going to start appearing in lots of applications, not just we're going to be doing only AI, we're going to be mixing AI with everything, right?
Yes, exactly. Just like how FPGAs are broadly used in a variety of applications, this AI-accelerated FPGA will have the same appeal as well.
Cheng, Wang, thanks for a great explanation.
Thank you.